before the end of the lecture today. It uses structured analysis. It's based on structured analysis as a foundation, and it uses virtual representations similar, very similar, in fact, way too similar. Diagrams build on the ERD and the DFD concepts. It's easy to learn, and the standards are use common sense, and they're commonly used, actually. But a lot of it is common sense. So in terms of the methodology, it's popular because it's a reaction to the perceived shortcomings of all of the other things that we've seen so far in structured analysis, and it's good for larger projects because we have a lot more ways of expressing the project, and we can actually express it as a networking application, as a communication. I mean, we can basically show different parts, sequences, states, all sorts of different things that we can't show in structured analysis. So as applications get bigger and projects get bigger and designs get more unique, UML helps us modify the traditional techniques and helps us extend it out to create some new capabilities in terms of the diagramming. And data and actions are treated as equal partners instead of separating them out. In structured analysis, they're completely separate. We talk about processes and we talk about data. In object-oriented analysis, we put them together, and now they're equal partners and they're working together, and the diagrams are showing both together, which is kind of interesting. Some diagrams actually don't show equal weight. As an example, a class diagram is showing the same thing as an entity relationship diagram, which is showing processes and data, but primarily focused on the data component. Same kind of feel, actually. It's really data-centric. And then, we have other diagrams that are going to be showing the processing part. So, in terms of the object-oriented analysis, we know about the object. It is the entity that I've been talking about for the last couple weeks. Entities and objects are identical. They're the same thing. And so we have the data, then we have the actions. So objects, although entities and objects are the same concept, object orientation extends the entity a little bit, which is why it got a new name, which is why it called it an object. Added 3 components to it. One of the components already existed, which was the identity. So all of the objects, all of the entities, they both have identities. Identities is nothing more than the name of the object or entity, like employee, class, student. Then we added 2 other components to the object that didn't exist in the entity. Those components were states and behaviors. Because in an entity relationship diagram, we don't show states and we don't show behaviors, we show relationships. In the class diagram, we don't show relationships, we show associations, and the associations have states and behaviors. Because one object associates with another object. A student takes classes. We have a student object, we have a classes object. And there's data that passes back and forth, and the name of the class, what days the class meets on. And then there's actions or behaviors. Students actually are taking, students are failing, students are passing, students are doing something in association with the class. So in the object we have 3 instead of 1 characteristic to keep track of is really the big difference. So in terms of the object, what are the data? The data, in terms of the data, we're looking at the attributes, and these are other words that they are used for representing the data concept. A lot of people, I like to call them data members, because data sounds more like what it is. Some people like to call it attributes, states, state variables. Most object-oriented textbooks are switching to fields for some reason. I'm not quite sure why. When I say fields, I always think of a database. I don't think of an object. I always think of data when I think of an object. Or data members is the vocabulary that I like, actually. And then we have actions. I don't like to use the word actions either. I like to say member functions, data member functions, because it kind of is like what is an action? Well, it's really a method or a method. Or a message, so sometimes called methods, sometimes called messages. So there's no consistency in the naming of these items. It's the concept that you want to be familiar with. And they're nothing more than actually what's missing above here are properties. So these could also be called properties. I was just looking at that a few minutes ago. And then actions, what's missing here is the word message. So messages, methods, member functions, functionality. So objects are independent units. They have a conceptual independence, and they also have a physical independence in the system. So if we keep that in mind, we basically create an entity relationship diagram that looks like and resembles an object diagram. It turns into an object diagram. Essentially, it's showing the same thing, and then you add the extra information to it, and you have an object diagram. So where does this all start from? We have many different methods that exist. And what I just went through was kind of a classic way of translating an entity relationship to an object-oriented diagram. Well, these other guys have other ways of doing stuff. In fact, that's the Brock method. He's the one that takes everything from structured analysis and puts it into. And most of my lecture notes are based upon his theories, because you go to a bookstore, you see Brock method for this, Brock method for that. You see his name is going to be written all over the place. OMT, you don't have to say very much of that at all. Maybe about 15 years ago, you saw a lot of it, and then it kind of faded away. Not very acceptable. It's kind of different. Object method technologies, stuff like that. It's just not very, like, I don't know. These guys down here, this is entity relationship dudes. These are these guys here, these two on the bottom, they come from structure and analysis and design. You open up Visio, you open up a SmartDraw, one of these tools, and you go entity relationship. You see these guys. And usually everything is labeled by the last name. This is the guy's last name who came up with the method. And it's just one way of expressing object orientation. And they're all researchers in the field, and they've all got their own interpretation of the concept, because concept's not standard, actually. All of them are essentially the same. They're all equivalent in terms of what they're doing. But this diagram's called this, that diagram's called that. This is how you're supposed to do this. This is how you're supposed to do that. Different ways of thinking, different ways of viewing. One of these days, hopefully in the future, it might become a standard. I personally think it's going to go away, actually. I think object orientation was, kind of the hip word for a while. Everybody's object. It's kind of like the use of the word engineering in the United States. You had a sanitation engineer, this guy who cleans the floors, the toilets. You got the computer engineer, you got the software engineer, you got the, and it's just an overused word. So now we don't actually have an object-oriented database on the market. It does not exist. Everything is relational at this point still, but just as a side comment. But we have object-oriented databases. You open up the box that says object-oriented database on it. Wow, really? Doesn't exist in theory. All right, so nowadays everybody represents object-oriented analysis using UML. That's another unified modeling language. What's UML? Nothing. It's just a term. Everything's UML now too. You draw a little stick figure. Oh, UML. I know UML. It's just an overused acronym for unified modeling language for object orientation. 3 steps in object-oriented analysis. This is the Brock technique, actually, if you study his material. You have to take basically the kind of the same approach as you do with structured analysis, but you're using objects instead, and you're kind of following through on a methodology in terms of steps to perform analysis. So if you were prior to object orientation, first thing everyone does is create an entity relationship diagram, create a design from a data flow diagram, flow chart it. What you're doing is the same similar kind of concept. You're putting all these words and you're taking it from the requirement specification and you're putting it into a picture. So you draw a picture of it because it helps you understand it. And it's more of a routine or an activity that helps you visualize what it is you're building and understand it, and then also share it with others. So there's 3, I don't know if I want to call them steps, I'd say components, maybe. Components to the process. And they kind of go in an order of precedence in terms of which ones are usually happening first, which is why it says steps. First step number 1, most people would take a use case modeling approach. Say, well, okay, we have this piece of software that we're trying to learn about that we're going to build. How do you use it? What's the user going to do to it? So you start out looking at it from a use case scenario approach, or use case modeling, if you want to consider it as the type of modeling that's being done. You determine how the various results are computed by the product without regard to the sequencing or anything. It says, okay, this product is going to be used for, it's an ATM machine. It's going to be used to dispense money, to accept money, and all the different usages. Largely action-oriented, as you can probably notice. And then once you understand how the system is going to be used, then you take it into an entity approach. This is sort of skipped in system structured analysis and design. So we added a step right in the beginning, and we said, figure out how you're going to use it first, which does not replace the requirements documentation. Everything is still based on requirements. But a lot of students think, oh, if I'm doing UML, if I'm doing object-oriented analysis and design, I don't have to create a requirements document. Yeah, you do. This is totally something. This is just your analysis. All right, so then you take it from that point, from a use modeling and action-oriented modeling, and then you look at it from an object modeling perspective. So you start doing a class model. So you determine the classes, their attributes. This is purely data-oriented. So in essence, you're sort of doing the same thing. You're looking at it from a processing point of view. You're looking at it from a data point of view. But the diagrams that you're creating are including both components together instead of one and the other. Because the modeling, the diagrams that are created for use cases are looking at both merged together. But you're still taking the same approach. And then we have the dynamic modeling. We actually do this in structured analysis and design as well. This is where we determine the actions performed by each other, by or to each class. It's purely action oriented. And then we repeat the process over again. So we're looking at processes, we're looking at data, and we're structuring it together. So let's take a look at the category of what these models, what these things are actually showing. Just start out, let's look at an elevator problem. We're going to run through the steps for object-oriented analysis to put together diagrams to represent, we're building software for the elevator as an example. This is a use case model, use case diagram, and sometimes referred to as scenario or scenario planning. It can be written out graphically, or it can be written out in a series of steps, as I'll show you. What we've got now is a generic description of the overall functionality. We have an elevator. We have a user. Yeah, people draw stick figures. Actually, you can get the tool sets and they have the stick figures in there for you. Some of them have a little hair on them. Some of them have like gloves on and stuff. It's actually kind of funny. Then we have the elevator, and then we have a press an elevator button or press a floor button. That's what the activities, the actions in which the user can perform. Gets comprehensive insight into the behavior of the product, theoretically. Well, what if you didn't know what an elevator did? You probably didn't know there. Actually, some people don't know there is a floor button. Yeah, they just press the start and the stop. Can you take me to this floor? Okay, stop. Now you see people, kids do that all the time. They get in the elevator and they press all of the buttons. You go to all the floors. All right, so here's the use case scenario that comes from the use case model. That's called a use case model. That's called a use case model. Looks like scenarios though. Not necessarily a diagram. But this is actually equally as important because this leads us to our test planning, our test cases. This is the concept of the use case. So then people, what in the world is a use case? It's nothing more than a line item or a scenario. I hate to use the word scenario because that's what this is saying. Functionality use by example. So as an example for the scenario, number one, I'm just going to read number one. A user A presses the up floor button at floor 3 to request an elevator. User A wishes to go to floor 7. Okay. And then when they get in the elevator, the up floor button is turned on. And then it basically goes through a series of steps. So you can take this and understand the functionality that you're building into the system, and then you have something to build the test documentation from. I'll be talking about testing in maybe next week, maybe the following week. Kind of give you a feel for how the testing can actually be automated right there from analysis. So, believe it or not, that is all that's involved with use case modeling. It is fairly simple. You can see textbooks that give you like 200 pages on use case modeling. I don't know why. It's like one of the most misunderstood, made to be overly complicated concepts, when essentially that is the concept right there. We create use cases, we create scenarios, we create stick figures with arrows pointing to things. So it's not that kind of complicated. Neither is the class model. So class modeling, we extract the classes and their attributes. We have those already. So if you've already done an entity relationship diagram, you have the classes and their attributes. Now you have to add the data that's associated with it and the actions that are associated with it. You know the actions because you've done this one. So you've got all the actions. So this is how UML, actually in object-oriented analysis, puts the pieces all together for you. It makes it kind of simple. Because you would still start out and take the entity relationship diagram and you would still create, let me rephrase that, 99.9% of the time, making the entity relationship diagram helps you 100%. And people will do it even if they are doing an object-oriented design. Half the amount of time, maybe 50% of the time, people will take the next step and do that data flow diagram. It's thrown away. If you're going to do the object-oriented analysis, you throw it away. So you may not necessarily want to do a data flow diagram if you know you're going to create an object-oriented design. But how do you know you're going to create one until you're all done? So it's like kind of a catch-22. After you've analyzed the system, then you go, this would lend itself well to an object-oriented design. Or you would say, you know what, that's ridiculous. And believe it or not, there are many, many, many different applications that do not lend themselves well to object orientation. Just think about any module going on a piece of hardware. Think about device drivers. Think about systems programs. Think about interfaces. Think about operating systems in terms of like what you'd stick on a memory unit for a microwave oven as a controller. Why are you going to make it not? Object orientation is really great for huge distributed applications and for a lot of the internet development right now, but it doesn't lend itself well to everything. And you don't want to decide that before you start analyzing it. Yeah, I'm going to write this little device driver that makes my mouse work on my iPad. I'm going to take an object-oriented analysis approach. Waste of time. In fact, complete waste of time. In fact, because it already exists, but anyway. Represents them using an entity relationship diagram. Yes, so you already have that. You already created one for your project. And you deduce the classes from the use cases and their scenarios, as I mentioned before. We get the data and we get the actions, and then often there are many different scenarios that are associated with it. And then the two approaches to class modeling. I think I've done this with this class already. Did we cover noun extraction already? No? Well, maybe it was another class. I don't know. CRC cards? No? Oh, okay. All right, so here's for the brand new people who have never studied object orientation, has never taken an object orientation or design course. You don't have to know anything about object-oriented programming to create classes. In fact, those people who don't know anything about programming create a better set of classes because they're thinking outside of the box. They're not thinking like a programmer. So analysis. Let's take noun extraction as an example. We already have the concise problem description. It's called our requirement specification document. We take that, we pull it out, dust it off, take a look at it, and we go, oh, we have sentences that are describing what is in there. And for our elevator control button, one of the sentences in this document says, the buttons in elevators and on the floors control the motion of N elevators in a building with M floors. So we have a number of elevators with many different floors, let's say. And this is how it was worded in our request. I don't know who wrote that, but some scientific-oriented person wrote that. And it's in our requirement spec. Then the first step we could do is if we're taking a noun extraction kind of approach, and a lot of people just do this mentally. You look at that and go, oops. You look at that and go, buttons, elevators, those are nouns. Yeah. Floor controls the motion. We have elevators, we have floors, buttons. Okay. So we come up with a list here, and our nouns are button, elevator, floor. We've got movement. We put movement in there, building. And then here's what happens when you generate a lot of information. It's kind of like, it's a brainstorming technique. And this is a big old list of nouns. And then we decide which ones, are similar. We can reduce it down to as few nouns as possible. Or let's just kind of create a couple that we know are going to exist. We know there's going to be an elevator, and we know there's going to be a button. So we kind of mentally, I don't know if anyone really writes them down, we just mentally look at the list and go, elevators and buttons, let's start there. So then we take and we draw out, this is our first iteration of the class diagram. And we have elevators, buttons, floor button, elevator button, floor button, button, and elevator. Looks like an entity relationship diagram. This arrow is kind of senseless. I mean, we could probably take the arrow out if we wanted to. Don't normally see arrows in class diagrams. I've been meaning to edit this for years and I have never done it. But I should take that arrow out because it's kind of confusing. You need additional classes because you need the elevator controller. So this is not what I would call a first iteration perfect diagram. No, you can't use this noun extraction technique to do this. In fact, none of these techniques actually give you a good diagram without some iteration, without some repeating the steps again. And you can kind of see where you get the one to many. You know, one elevator communicates with many different elevator buttons, maybe, or I don't know, maybe different elevator buttons communicate with one. And then we have the floor button that communicates with the elevator, and you can kind of see how that system sort of works together. It differs from an entity relationship diagram because now we have 3 sections in the box. We still have the identity here. We've taken it a step further, and we're guessing right now, and this is all guesswork actually. And we said, you know, well, let's talk about the data, and now we have the data and we have the actions that are associated with it. So the data illuminated. We want to keep track, is the button illuminated or is it not illuminated? And then here on the elevator, is the door open or is the door shut? You know, we could make that into 2, we could make that into 1, but we would list any known data at this point in the second. We always put the identity, the name in the top box, the data in the second. The third box is going to be actions. So we decided on the first iteration that we needed to add an elevator controller. That the elevator controller didn't exist, which we can't tell from the noun extraction that we need a controller. So, and actually, as a side note, this is why we have model view controller. It's another methodology, another breed of junk. No, I was going to say junk science. It's not junk science. Another breed of science that lends itself well to a modeling technique, so we can actually look at the models in terms of classes and control over the classes and interfaces to the classes, which is a different technique completely. If you can take an entire course. Actually, you can probably take an entire major in object-oriented analysis at this point. And you can go to the library and you can find tons of books on this as well. But another approach is called the model view controller, which is abstracting these components out into those 3 areas. So the second iteration, what we've done is we've added this elevator controller in here. And we put it in here to say that the elevator controller is going to control the elevators. One controller is going to control any number of elevators that might exist. And now that we have our second iteration, and our third iteration, we've added, let's say, a little bit. What do we add? We have elevator doors, button, elevator button, floor button. Oh, we took out doors? I thought we had doors in there. Or maybe we didn't have doors. I don't know. We put the doors in here now. It doesn't really matter, you know, what has changed in the diagram. The concept is we went from 1 to 2 to 3. We've got different versions, all theoretically showing the same thing, sort of, you know, kind of. So the elevator controller controls an elevator. So why is iteration needed? Perhaps the method is not yet mature. Also, we have this brand new method, better than sliced bread, called object-oriented analysis and design. Yeah, why do we have like 5 different researchers and 5 different approaches and no standards? Well, because it's not really proven. And it's not a standard. And it's just a methodology that somebody said, oh, look, it works good. And now we have object-oriented programming languages that use it. But that's why I say it's probably going to go away in the future. It's going to be called something else, or it's going to translate into some sort of a formal structure, because we need iteration. We need to go through, and it's like taking a dartboard and randomly throwing darts to see what you got, because it's guesswork in a lot of ways. But yeah, no, it's not very mature. I skipped over what was called CRC cards. I thought it was in this. Yeah, here it is. Actually, it's next. I want to cover CRC cards a little bit, but that's extremely outdated. And actually, I'm going to cover that first and then come back to iteration in a second. But CRC cards. 1989, object-oriented analysis. This is very, very, very old. This is like one of the first techniques. And they said in the beginning, in the way beginning of time, people thought object-oriented analysis was going to be so easy to learn, and it was going to be the quick and easy way. There's the thing about the generation's programming languages. We started out with assembly language, right? That's really hard. Well, machine language, assembly language, a little higher up than that. Then we ended up with C. And we're going to go through the entire language hierarchy. Eventually you get higher and higher and higher, and they call them generations. So now we have 4th generation and 5th generation language. You just point and click and you create a program, you know. Well, object-oriented analysis was supposed to be like 4th and 5th generation, although it turned out to be a little bit more complicated than that. And a couple of people in the beginning decided, well, let's create this, and this is how Smalltalk actually started. Let's create this as a language for kids, for kindergartners, to build and program software. Okay, because we could teach kids at the kindergarten level to understand object orientation, and this is how we're going to do it. So they had building blocks. They were all different colors, you know. Everyone's played with, kids play with Legos, building blocks, and the spatial orientation. They take the blocks and they build structures with it. Well, that's object orientation if you think about it. So you say, well, let's put it on the computer, make it for adults. So we take the blocks away, and actually, it was actually kind of proven that the kids could build software programs by arranging the blocks and pulling blocks out of a bucket. So you had to pull a block that you needed, which is an object. So if you needed a bridge, you had to pull a bridge out, put the bridge in there, and you had a pond out of there, and you had different objects that represented different shapes and sizes and things, and you built this scene from it, which is what you're doing when you're creating a software program using object-oriented analysis. So this concept of CRC cards, we created a card that had 3 sections on it. This is how the class was actually divided out into 3 sections. And this is how the object came about, how the object was born, essentially. We have a name. Well, that's the identity, the name of the class. The second one was the functionality or the responsibility. That actually later on turned into data. Because you think about it, elevators, what are they an elevator button, what responsibility does it have, or what functionality? It turns on and off a light, and so the light is on or off. So represented in a kind of a data-centric kind of perspective, functionality, or R for responsibility, was what data is this class responsible for holding? And then we had collaboration. Well, what is collaboration? Talking back and forth, communicating. The communication method between different classes. So that ended up being the 3 sections of the box of the class model, which ended up starting out as a CRC in terminology, which ended up coming from the concept of building blocks and kids playing around with toys to build stuff, which is essentially what we're doing in object-oriented analysis. So the strengths, the way this was implemented originally is you take out a 3x5 card. And people actually still do this. It's usually a teaching kind of method. You know, some schools, undergraduate level, usually, it's a lower level kind of, nitty-gritty details about how to create a class. You take out a 3x5 card and you put 3 lines on it. You divide it into 3 sections. You put a name for the class. You put the data, and you put the responsibility. You put the collaboration underneath it. And then you have all these classes, and then you can take the classes just like the building blocks, the 3x5 cards, and you can arrange them on the table. It's a physical way of taking, cards, actually, which is why they're cards. You arrange them on the table, and then you can actually physically see it happen instead of drawing it out, mapping it out on a computer. And then you can draw lines if you wanted to on a piece of paper underneath it, and you can kind of see. And then you can see what cards are missing. I'm missing functionality. Missing, so you add another card. You add another card. How many duplicate cards do I have? Oh, look, I have 3 of them that all do the same thing. Well, just get rid of one. Take them all away. Just have one. Get rid of the rest of them. So it actually is the same process we go about in terms of programming and object-oriented style. Actually, same process. Weakness: the domain experience is needed. So if you don't know about programming, you can tell a kid to create a house. You can tell them to create, a bridge or something, but you can't tell them to create an accounting program. Because how do you know what you need in the accounting program? So you need accounts payable, accounts receivable, I don't know, reports. That's all I know about. And that's all I keep mentioning in terms of accounting. That's why I bring up accounting, because I have no idea what accounting is all about, really. Although I do balance my checkbook. But so here's an example CRC card, as I mentioned before. We got our 1, 2, 3 sections. The section in the middle is big. And this is the CRC format. It doesn't necessarily lend itself to the data. So, or into the methods, as an example. This would get translated into what would be called the class methods and the class data members, or member functions. So here we have, turn on elevator button, turn off elevator button. Well, that would be button, boolean, on or off. let me know which one it is. And then down here the class elevator button, well, that would be a collaboration. That would say get or set elevator button. And then we have the floor button, get or set, turn on floor button, turn off floor button, or elevator, which floor are we on? And so we can kind of take and we can kind of translate that essentially into our 3 common sections of the class. This is not a class. It's a CRC card as a second iteration. So let me go back to the iteration again. Even if we're doing CRCs, we got to do iteration because we have to look at it, add another card to it, add another card to it. And so most of what we're looking at in terms of weaknesses applies to all of our models so far. And here's another example in terms of the waterfall model. Why do we have feedback loops? Well, because it's not a perfect model either. We learn from each stage in the development unless we go back and provide feedback to the previous stage. We can't learn, we can't basically be perfect at it. We're going to make mistakes. And if we don't consider feedback, we end up shortchanging the project. Rapid prototyping model aims at reducing the iteration, and instead we end up with a junk product at the end because we didn't go through anything. We just started and we hacked away, and we got garbage in there. So we end up rebuilding that from scratch eventually to fix it. But we've learned about the concept and we've developed it to a certain point. Spiral model is sort of very similar, but instead of assuming that we're going to use a waterfall staggered approach in the spiral, we just put it all together and say, okay, we're still doing requirements. We haven't finished it yet. We're still doing analysis. We're implementing the product, but we're still working on the requirements document. So it just does things parallel. Iteration is a property of software production as well in terms of medium and large size projects. Especially if there's a lot of dollar value, a lot of time associated with it, you're definitely going to take advantage of that. And it's also object oriented. So iteration is expected. So you have to expect iteration in terms of the object oriented platform. So dynamic modeling, our next category of modeling. You produce a UML state diagrams, not the same as an activity diagram. So it's a little different. In the state diagram, we have a state, we have events. We can have a predicate for like maybe distributing over a particular state diagram. Here's the state diagram for this elevator. It doesn't look that complicated, but compared to some of the other diagrams we've seen so far, it's probably the more detailed one coming up. We can't do this in entity relationship or data flow modeling. It doesn't exist. So this is new. And what is this doing? Well, if I were building an elevator module software program, I'd be interested in the states. Otherwise, what happens? You have to troubleshoot problems. The elevator is on the 5th floor. How does it get to the 1st floor? It's got to go through different states. It's got to go through the 4th, the 3rd, the 2nd. It's got to go down. It can't go up. So the controller's got to know, are we lifting the elevator up or are we lifting it down? Well, that depends on what floor we're on. So the different states might be important in terms of the design of the application, and if I were building this, I'd do a state diagram. If I were building an accounting program, I don't think I would do a state diagram. Of course, then again, I already said I don't know anything about accounting. But I'm thinking that, there are some different transitions. So when customer pays a bill, then that's more action-oriented, I think, or more activity-oriented versus state, actually. So I don't really see any states in terms of changing them, in terms of activities. But essentially, you could model states. In terms of the modeling tools, as I mentioned so far, you're going to need to pick up something for the class, for the analysis document. We have actually, I don't know if it's 30 days anymore. I think it's 7 days now. SmartDraw. If you're really interested in all this stuff, SmartDraw's not that bad. It's like $39, I think, or $40. You get a full lifetime, I don't know, until it expires, until they come out with a new version. Microsoft Visio, another point, and I did actually check on Dreamscape as a Microsoft Dreamscape for the university. We are filling out the application form for it, but we might have to wait for the candidacy status for the accreditation before we get it, but who knows, we might actually get it earlier, because some high schools actually are part of this and they don't have accreditation from MOSC. So System Architect no longer exists, but there's old copies of it out there. It only works with older DOS versions, doesn't work with newer ones. Case tools, many other drawing tools on the market. In case you're interested in what these drawing tools are doing, what they're offering, And this is where it comes in handy, especially if you want to create all sorts of UML diagrams and you have no idea what exists. You hit the UML button, and he goes, oh, look at that. Here's all your diagrams. Whoa, that's a lot of diagrams. So in here, usually this is Smart Draw, actually. The reason why I like it is there's software design. I want to design software, or am I going to do benchmarking, organizational charts, flow charts? It's all categorized out in terms of the type of diagram you want to create. And here's an example of the entity relationship. You got a plain old, generic entity relationship diagram. Or you got a couple different data flows to choose from. Or you have a database design one up here. Or you've got, a bunch of other stuff to pick from in terms of authors of different pieces. What are they going to give you? They're all pretty much the same. They're just going to give you different styles of tool sets. The box might have rounded corners instead of solid corners or something. Or there might be extra spaces or something like that. In here for the data flow as an example, we've got the opening and the closing. We've got you can see that on the screen, we've got the spot for the number. We have different styles of boxes here with open. Both of them are open or just one side's open and stuff. So you can kind of see what that looks like in terms of the design of the tool set. And a tool set is only essentially going to give you, am I still recording? Good. Last weekend I was recording and the record stopped and I lost about 3 hours of lecture. Now I'm paranoid. I'm like, am I still recording? I was just taking it for granted before. I'm like, yeah, this is recording just fine. Like 2.5, 3 hours later, I'm like, none of that was recorded. Ouch. So, we're not done yet. This is part 2, lecture number 8 of object-oriented analysis. And we're going to look at more UML diagrams is what we're going to do in this lecture. So what do we have here? And just kind of a little repeat at the beginning, because you can use this in I can use this lecture for different settings, but I'm recording it all together. So Unified Modeling Language, we all know what UML stands for already. But what is it really supposed to be doing? And this is why we have so many different diagrams. And kind of the theme of this particular lecture serves as a bridge between the requirement specification and the implementation. So it takes everything, hopefully, out of the requirements. So it depends on what's in your requirements. What is you're actually building as to what kinds and what types of UML diagrams you're going to want to create. Provides a means to specify the document and the design of the software system. It's process and programming independent. So that's another mistake a lot of students think. They go, well, I'm designing this for Java, or I'm designing this for C++, or another object-oriented language. And the problem is you're not designing it for any project, or any programming language. It's a methodology used for the analysis. It doesn't actually give you a design, and it won't give you a design that's specific to any language. Particularly suited for object-oriented programming development, but it doesn't have to be used in object orientation. However, if you're going to do object orientation, you're going to take this route, hopefully. And if you take this route, you might decide maybe you want to do it in object orientation eventually. So it kind of lends itself well in terms of translating into objects and that turn into classes. So we've actually seen so far object diagrams. If we will take it a step further, we can translate the object diagram into the class diagram. Class diagram has the same 3 components: names, attributes, and operations. Or you can call them name, data, members, and member functions, or properties, or put any of those names on it. But for the purposes of this lecture, we're going to call them attributes and operations. And so now we look at, some people actually like to put data types in here too. You don't have to. In fact, my recommendation is don't put anything in the diagram that doesn't need to be in the diagram. Because if you put a data type here, for example, size, and you said integer size, and you put that in the diagram, and then you realize, well, we could have half. We could have 1.5. 1 3/4 is the size. But we've said integer. So now we've restricted the entire design and implementation of the software to make it in whole integer values instead of using floats or doubles or something to show precision. So we're stuck. So something like that could actually cause an error, cause a bug in the system. So believe it or not, the methodology is kind of interesting and the philosophy is sort of interesting, meaning less is more. The less you put in there, the more the programmer can think and actually implement it correctly. The more you put in the diagram, the more restrictive you make it, the less the programmer can actually do. less freedom, less interpretation, fewer, more problems essentially. Here we use the notation of the opening and closing brackets down here. We don't actually have to, but this is done to reiterate the point that these are methods, these are functions. So this is pretty standard. We'll see open, close, move, something like that. Just single word. You don't put a diatribe in here. You don't put your life history. You don't put everything the programmer ever wanted to know about the software in here. I have seen people put in requirements in here. This class does this, and it does that, and it whoa. It's like too much writing for a diagram. Although now you're able to write more on the diagram when you use UML. You don't want to turn this into a 3-page document. It's a simple class. So here's a class. It's a description of the set of objects that share the same attributes, operations, relationships, and semantics. Then we have this thing called an interface. And the interface notation is a circle. And it says is spelling, or I spelling. So an interface, by definition, and here's the definitions that are underneath it here, collection of operations that specify a service of a class or component, externally visible behavior of that element. So if you took the Java course, Object-Oriented Analysis in Java, we talked about it, and we created interfaces. I don't know if you had to do any for your assignments, but I talked about interfaces in the class if you took that class. It's the same concept, it's the same meaning. We have that in Java, which is a pure object-oriented language. We don't actually have the same concept in C++, which is kind of weird. But C++ isn't truly object-oriented. It follows an object-oriented methodology, but it's not as true to form, true to the methodology as Java is. But the interface is it says this class interfaces this other class, which means it implements that behavior. It works with it. Nope. Interface, separate concept. We have interfaces, we have classes, we have interactions between classes. This would be a template for a class. Some languages actually refer to the concept as a template. It really isn't, though. An interface means that it's kind of, are you familiar with C or C++? It's like a .h file, a header with a C++ implementation. It's kind of like a the way that it's implemented in C++ is that it's a specification is the .h, and then implementation is the .c++ file. And so I would have like my class.h that would specify out all of the different methods that were going to be in this class, but it would not have any method bodies or anything. It would just have, this is the functionality. And then my class.c++, the implementation of that, and we're good, if you're taking a C++ class, I'm going to cover this in the next couple weeks, and then, that would be all of the method bodies filled out completely. And we have single to single. We have this .h that works with this .c++, and we have the template, but it's not really a template. It's not called a template. It's called the specification and the implementation. And so it is. It's also considered a library file, but when you start making your own classes, you're making your own libraries. In fact, if you look at the .h files for things like iostream.h and string.h, you see the specifications. You don't see the implementation. You won't see the source code for all of those methods. Instead, you'll see the shorter version of it, the stripped down. This is just what these methods are. We have a cin, we have a cout, we have all of this stuff, right? And then in there we have a compiled.o file of the C++ file that uses that interface. It uses that template that gives us all those methods. And when we include it, we don't include everything. That would be way too much. Instead, we include the .h file. So that's where our includes are at the top of the source code, and we include it. And then the compiler looks at it and says, oh, we're including iostream.h. Oh, there's a cin. Now here's the cin. Go get that object code. We need cin. And compile it along, include it along with, which is why it's called include it along with the other source code that this programmer has written. So Java says it implements this, it implements that, and these are the interfaces that it's implementing. Same kind of concept, except for everything is a .java file because everything is a class. Everything's stored in the same kind of format. So we don't have .h's and .c++'s. Instead, we have .java, 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 and they call it an interface. And then so one class can interface, which means it's going to implement functionality of C in, C out, or all this other stuff. And it's different from inheritance. It's not going to extend another class. It's not going to build on that behavior. Rather, it's just going to be required to implement it. If you have something in a specification, it has to be in the implementation. So if I were to write a brand new specification for iostream.h and I were to leave out, or actually I put in something new, like a CC out or something instead of a C out, I would be required, the compiler would come back and give me an error message if I didn't put in an implementation of that method that I included in the specification. So interfaces is basically a way of requiring rules. And that's where this last few minutes of discussion brings up an excellent point. This is what makes object-oriented analysis difficult. It takes domain experts. It takes knowledge of the programming in order to actually do the design. It's like a catch-22. In order to analyze it, you have to know what tools are available, right? And you have to know about interfaces. So it's like, how do you take and create, how do you get the business people to design object-oriented programs when they have no idea about object-oriented programming? They can do some to a certain point, but when you start working at this level, then you start looking at, well, how do I know what an interface is? I don't even know how it's implemented. But what they've done, and they've actually done some studies with this, is they've taken people who are business background, no programming experience at all, teach them what the concepts are. This is an interface, that's an extension, that's a this, that's a that. And then they can actually put the pieces together, no problem, just the way grade school kids could put blocks together and build a program. So, because what you're not doing is you're not specifying out everything that's going to be in that .h file. No, you're just saying that this is the concept that you're going to use with that file or something. Right, so the interface, collection of operations that service the class or the component. Externally visible behavior of that element is the interface to it. We could actually think about public, private, and protected interfaces as well, but I'm not going to take it that far, because this would turn into a programming course instead of an analysis course. But there are some components associated with that. If you are familiar with different types of interfaces, then we can extend the concept further. Collaboration and use cases in terms of the notation. We have a chain of responsibilities that's in a collaborative chain of responsibilities that we show in dotted. Why? Because, okay, so it's not solid, it's open. So things can go in and out. And multiple things can collaborate together inside of this bubble that we're representing. And generally we have areas that are in a circle. We have different items inside here in terms of the notation. And so collaboration defines an interaction, society of roles, other elements that work together to provide some sort of cooperative behavior. So the elevator controller doesn't work on its own. It needs an elevator button. It needs an elevator. It needs something, So those things we could draw if we had like an elaborate program. Let's say it was for the entire hotel or something, or entire building. And we had a water system, a fire system, and all this other stuff. We could draw this type of circle around things that said, "Here's our collaborative. This is our elevator." And we have a collaborative kind of effort going on between all these different items in here that are creating that behavior. And then we have a use case. We've seen those before. We just have a circle. So let's place in order. So the use case is a description of a set of sequences of the actions that a system performs that yields an observable result. It's activities in terms of our regular use case. And then we have ways of saying active classes versus inactive classes, and we just put dark circle. Yep, interaction between groups of classes that collaborate together can be shown in the diagram. You're just basically drawing a circle around them, but you're leaving it open to show that it's not a use case. It's not one activity, it's many occurring simultaneously. And why they use this notation, I have no idea. I know the terms, but I don't know why they use the symbols that they use. I could probably I don't know. And this is what makes it as well. This is what makes the concept a little difficult. Not only do you have to know about object-oriented concepts, but you have to know what is it that you're trying to represent in the diagram. And then when you look at the diagram, it's not going to look like an entity relationship or a data flow diagram. It's going to look more complicated than that. So in terms of the notation for an active class, we're looking at nothing more than a darker. So we have, and then an active class is a class whose objects own one or more processes or threads and therefore can initiate control activity. So the elevator controller would be an active class in that entire system. It's not going to be passive, so it's active versus passive. Passive, you call the button and you illuminate it, make it red, make it green, and then it goes away, it goes to sleep. And then when it's asleep, it's waiting. And then, but at any one moment of time, depending upon what you're trying to show, the elevator controller would probably end up being active again, and that would be doing something. Think of it, if you animated this as an example and you started running the program, certain classes would illuminate. In fact, they make demonstrations out of this. They go, the elevator controller, woo, and it gets brighter. Goes to the elevator, woo, elevator. Now the elevator controller is now dull, and this one's lit up or something, and then you kind of say, ooh, look at that, and it goes to this class over here, and it kind of bounces back and forth. That's all the diagram technique's doing. But you're doing it statically instead of like in a dynamic demo. So here's some more notation for you. We have things that we don't have in entity relationship or structure analysis and design. We have components, packages, nodes. Let's talk about the component for a second. It's a physical or replaceable part of the system that conforms to and provides a realism. A set of interfaces. That's what a package actually sort of is, or a library, or an external component that's being used that's giving you a set of interfaces. And then we have this down here. People go, why in the world am I even showing this? It's a node. You can show nodes like servers and clients. They're not really classes. They aren't really objects. They're just items or nodes. So a node is a physical element that exists, runs time, presents a computational resource. So a lot of people would put the server and it's just a box. And they don't make it a flat box because then it looks like a class. So instead you give the box dimensions to it, and then all of a sudden you have a new symbol. And how this component is supposed to like tape on and tape off, I guess. I don't know. You're supposed to be able to connect them together in terms of components. And then we have behavioral things. So these are the connections that we're doing in terms of the collaboration, in terms of the sequence. Yeah, we have an arrow. Arrow's not too bad. We see that in data flows, we see that in entity relationships, connects the boxes together. It's the interaction, it's the behavior of the components that comprises of a set of messages, perhaps exchanging any type of an exchange between two processes for any particular purpose. We connect the box with an arrow. Sometimes we use an arrowhead, sometimes not, but it's going to essentially show, an arrowhead's going to show the direction in which the message is being sent, theoretically. And then we have state machines. The weird thing about a state machine is that we don't have a rectangle, we have rounded corners on our rectangles, which means it goes around and around and around. I guess the box gets beaten up, and the sides, the corners of the box get worn down, I guess, because the box has been around, moving all this time. So it's wear and tear on the box. I don't know. Think of it any way you want, remember it any way you want. It's helpful when you remember the symbols because you look at a diagram and you go, oh, that's a state machine, or supposed to be, if they've written the diagram correctly. But then there are some tool sets that use this for classes. The classes all have rounded boxes. It's like rounded corners. And you're like, is that a state machine or is that a class? So the state machine is the behavior that specifies a sequence of states for an object or an interaction goes through during its lifetime in response to an event, like waiting, sleeping, if we're talking about processes or something. Then we have grouping and annotations. Yeah, we can put comments in a diagram. So entity relationship data flow diagrams don't normally contain any comments or any notes or anything, but we can put those in UML. We also have this concept. This looks like a folder of some sort. It's really called a package, which is the same terminology used with packages in Java as an example. We don't have packages in C++, but we have the same concept implemented differently. So package is a general purpose mechanism for organizing elements into groups. Java, it's actually directory structure that ends up being in a package, and we add our classes to packages, and then we include the we use the packages. So there are business rules, and this is why it looks like a kind of like a vanilla folder, kind of, because load every stuff in that envelope, that folder. And then here we have the stickum note with this, turned over. You'll be able to pull it off the page. Stickum note. So the note's a symbol rendering the constraint. It's attached to elements or a collection of elements, and it just appears randomly. It's just a comment. And then now we have our relationships to think about in terms of the diagramming notation. A dependency, let's say, semantic relationship between two things which changes to one may affect the semantics of another. So one is dependent upon another in terms of its relationships. And then we have it's really called a relationship notation, but it's really an association, which is the same symbol that we see in an entity relationship diagram. Same symbol is being used over again. But now instead of calling it a relationship, we call it an association, as I mentioned before in UML. And the association is a structural relationship that describes a set of links that a connection between or among the objects themselves. And we see employer has 0 or 1. 0.1 employer has employees. Any number of employees might be working for one employer, or no employers. So the notation is exactly the same as we saw in entity relationships, because it's really showing an association in UML terms, but it's a relationship. We also have child or realizations to think about. So what we've done is we've taken a simple entity relationship concept. We've expanded it out, gotten rid of the relationship. Instead, now we have dependencies, associations, generalizations, and realizations. You'll never see this because most people don't take the time to learn all the different ways. They just draw a line between this one, and they call it an association. And you don't have to know this for any exams or for any diagramming that you're doing in this class either, because if it's not really commonly done in practice, why grade you on it? But it is actually. You'll see more professional people doing it. And they should be. But if you don't have a child-parent relationship, you're definitely not going to take this route. But a generalization is a specialization or a generalization relationship. So it's a specialization. If you think about one class specializing in another class, this is used in inheritance, and it looks the same as a relationship, actually. One class. The shape comes from the object. The shape, from the shape, so we have object, shape, and then we have, let's say, triangle or rectangle. And we have these different shapes that are coming from, different types of shapes that are coming, and they would be represented with an arrow, essentially. And the solid one saying there's a direct one-to-one relationship, or a generalization or specialization. So the child is a substitute for an object of the generalized parent. And then the realization, which is the open line here instead of the solid line. So the semantic between the classifiers. So one classifier specifies a contract, and the other classifier guarantees to carry it out. Meaning, we're telling you to do this work, and that person's going to do the work. And we have nothing to do with that work. But this class is going to take care of it. It's like the print functionality that would go to a realization to a print module that actually does the printing. But we don't do the printing, we just send it over there to do the printing. So, outsourcing. So let's talk about some diagrams. So now we're going to see these symbols all put together. And you see the same set of symbols I just gave you a few minutes ago, and this is lecture 8 if you want to download it and take a look at it in more detail. Those all symbols, that's it. It's just repeated over and over again in different diagrams. So you'll see interfaces, you'll see generalizations, specializations, all sorts of associations, dependencies. Those are the symbol sets. And then you create diagrams out of these symbol sets. So what kind of diagrams are you going to create? Well, class, object, use case, perhaps interaction diagrams, another category, and maybe a sequence, maybe a collaboration. These are just a small subset of the diagrams that are available. If you get into like rational rows or something and you look at all of the different diagrams, there's hundreds of these things. Nobody ever knows. I personally can't even tell you how many UML diagrams exist on the market. Because it's not standard. One guy might have 20, the other guy might have 10. There's an infinite number probably, but I don't know. You know, people come up with these new diagrams all the time. Think about the methodology. It actually grows with the application domain. So now we have wireless. You know, 20 years ago we didn't have wireless or so. So now we have diagrams that show wireless connectivity instead of wired connectivity or something. So it's actually not a bad idea to be able to extend the language or extend the methodology to encompass new technologies. So keep in mind that the diagram is the graphical representation of a set of elements. So class diagram showing the classes, the interface is the collaboration objects showing the objects themselves and the relationships, the use case showing the use case and the actors. We've seen those already, but we'll see a couple of different examples, just more complicated looking ones that, you know, now that you understand what you're looking at. Interaction diagrams showing the interactions that exist between the objects, different from a sequence. So interaction would be more of a, this object uses this one and talks to this one all the time. This guy has no idea who this guy is down here. They don't communicate very well. You know, they don't have to. A sequence diagram emphasizing the time order, the collaboration, emphasizing the structural organization of the objects and how they collaborate together. State chart diagrams, we saw one of these already. That was showing the different transitions, events, activities that occur between the different objects. And then we have the activity diagram, which is a state chart type of system, but it's showing activity to activity within the system instead of transitions from states to states. Similar. Sometimes they look the same. Actually, it depends on what if there are no states, you're just going to have the activities going on. Component diagrams, this is what you have to do for your particular analysis document. On the UML section, you have to have one component diagram. Well, what's a component diagram? Well, it shows the organizational dependencies among a set of different components. You can have class components, object components, system components, subsystem components. If I were you, I would personally take your entity relationship diagram, strip out all the cardinality, make the boxes, you know, clean up the boxes if you want, and call it an object diagram, because that's what it is. And then there you go, you have your component diagram. So those guys who are listening to me right now, you don't actually have to do any UML diagramming for the analysis or for the design document, because I just showed you how to translate your entity relationship diagram into an object diagram. There you go. There's your component diagram. So then I have other people that will create all sorts of other things for it too. But yeah, there's a section. It's called requirements. No, it's called functional requirements, and it's section number 2. And in there you have one entity relationship, one data flow, one UML. But before the UML, you've got process descriptions of each one of the process bubbles in the data flow diagram. Anything you want. For the UML component, it's supposed to be a component level diagram showing some components of the system. Any component, well, an object is a component. So you can show it from component diagram, by definition, encompasses all of the components, and it's a representation of the components in terms of how they're being used in the system. Objects are components, so you can take and create an object diagram. An object diagram is the one, I'm going to show you actually in a few minutes, class diagrams, but object diagrams are just boxes. They look like entities. In fact, the entity relationship diagram is an object diagram. But the object diagram doesn't show cardinality. You can take your work that you've done on your entity relationship diagram, strip out all your cardinality, take out your diamond symbols, just draw lines between them, and there's your object diagram. So you don't actually have to do any UML, is what I was saying. To make your life easier. If you want to do them, if you created a use case scenario or use case diagram, that would help you with your test cases. So the interesting thing is these diagrams are supposed to be providing analysis and allowing you to learn about the system. It makes the rest of the work easier. So the more you diagram in theory, the easier everything else goes. In theory. It's all theory. Deployment diagram, you're probably not going to want to take that route because you're not creating it, you're not deploying it, you're not packaging it or anything, you're just going to build a prototype. But if you did that, you could show the configuration of the process nodes, the components that will live on the nodes, and all of the different pieces that you're creating. You can do that without deploying it, however. Hello world. This is the hello world diagramming component. So we have a class, we have the name, we have the operations. We've left the middle empty. It's okay. Because hello world doesn't actually have any data. What does it do? It just prints something, it prints hello world to the screen. There's no data associated with it. So that's our class. We can add an annotation. This is that little stickum note. Don't worry about what's inside of it. But this is actually kind of common. You see people writing, we want to use the g.drawString. Because this is a GUI version of the hello world. So we can animate it and say, this is what we want to do. We want to write hello world in a window. So we're going to use a GUI component instead from, And this line is shown dotted, meaning one is this, there's a, one uses the other. So going back to this dotted line over here, this is why this slide set's kind of useful. We have a realization that's going on here, and then a realization with an annotation. And annotations are stickum notes. This is our, with our, looks like a stickum note because one of the corners is folded over. So what we're doing is combining all the symbols in different types of diagrams. That's what I'm doing here. So, and then there's a source code that would come from that theoretically. So you could take that diagram for hello world of the abstraction and turn it into this source code. Realizing that we've taken this from the annotation. Uncommon to see this in the real world, obviously, because it's so small. But this is not what I would call something people would do. It's for illustrative purposes. Here's our class diagram of the hello world, where we have a generalization coming from applet, because we're building hello world as an applet. If you don't know about applets, don't worry about it. It's just, let's call it an object that provides a GUI interface instead of a command line one. And this is the same thing. We have dependency going on with graphics as another object that we're going to use. So this is no longer an annotation. This is another class, a class, a class. These are all three classes. If it's blank, just leave it as an open class or object. Don't put the extra lines in it. Then it looks incomplete. If I drew this applet and I put two separate sections in it, and then it would look empty. Kind of like how this sort of looks empty, but it looks even more empty if the whole thing's empty. So objects are classes. So we're just saying this object applet, we're not going to tell you what's in applet. I'm not going to tell you what's in graphics either. But that's how you would assemble a class diagram as an example. Now this kind of looks like your entity relationship diagram in terms of the system. If we were not modeling the application, we're modeling the system. We could say that hello world uses applet, and it extends or has a relationship with graphics. So these are actually relationships that exist. If you took your entity relationship diagram, you started backwards, took the entity relationship, you could translate it into this class diagram. And of course, you're not going to have paint in here. You're probably just going to have an object, an object, an object. So it would be an object diagram versus a class diagram. It would be the same thing. Here's our inheritance diagram, class inheritance. So interface over here, we have an interface, the image observer, that's implemented with component. And component comes from, everybody comes from object. In fact, this is the standard, this is where applet comes from actually. If you study object orientation, if you look at the graphics component of it, through the object line we have object, component, container, and then outside we have panel. If you took my object-oriented Java course, we saw that we had Notepad that came from, or multipad or whatever it was called, that came from panel, that used panel, container, component, object, that all came from object. But it's just a matter of what you're importing and what you're creating instances of. We create an instance of panel that sits inside of a container that sits inside of a component. And everybody's an object, so everything comes from object. And then we have applet that we could create that would be in a panel, as an example. And then we have hello world that would be in the applet, that would be in the panel, that would be in the container. Don't worry about it if you don't know inheritance, if you don't know anything about object-oriented programming, because that probably went over your head. But look at the diagram. This is what the diagram's doing. So it's just showing you the symbols put together. Here's our packaging of classes. Normally we would say import Java asterisk. Or Java applet is actually what we would do. Because applet is going to be used by hello world. So we can go java.applet, we're going to java.awt, java.language. These are packages that we would actually, that are part of Java as a base system. If you don't know anything about Java, that's going to be over, again, not going to make any sense. But those people who do know something about Java, this is how you're notating the packages, because you're using a packet symbol. And the interesting thing is on this file, as I mentioned before when I was showing the symbol, so it kind of looks like a file folder. Well, where you write on the tabs on the top of the folder where you write the name of the file. You know, this is Visa bills, phone bills. This is Java on our file folder, and inside we have these things, components, are all part of the package. Notations for classes and objects. On the left-hand side we have the class, on the right-hand side we have the object. You could take it a bit further. You don't have to. In terms of the names of the objects that are underlined, we have some examples here. An object, colon, any class. This is not what I would call standard Java notation. This is more C++ looking. Or colon, any class. Or, because this colon is using syntax that's very similar to scope resolution and things of, you know, resolving. Inside of this object we have this sub-object or this other object, or, you know, which we don't normally notate for Java. So, but on the left-hand side we have a class. Any class is the name, attribute 1, attribute 2, operation 1, operation 2, or just simply any class. If you get this far, you're doing great. If you represent the objects like this, you're doing great. Because most people aren't going to do this. It reads like Greek. What if you haven't picked out the language and you don't know exactly how you're going to represent it? You want it. The idea is to keep it simple. So when I create an object diagram, I use a class symbol, but I just don't include the subcomponents, because this and this looks the same, but I don't underline it. And you give it a logical name at least. An object, any object. Well, here's our any object here, but I don't really care where it came from or what object it belongs to. All right, that was lecture number 8 in terms of everything you ever wanted to know about object-oriented analysis, and we're doing good on time, which is good. I'm actually got a little early, so. Questions? Do you want to go back to the analysis document on page 46? Do we want to revisit the requirements for that? Are we familiar with that? Comfortable with it? Or do we want to do it next time? We don't want to answer. That's good. No news is good news, and we'll stop at that. So I think what